So as I was saying at the end of the previous session, scattering is all about the scattering amplitude. Sorry, I keep forgetting. Scattering is all about the scattering amplitude, your f of theta. And we had a formula. In fact, here it is. I've written it out again here. Here it is here. So it's a formula relating what your the scattering amplitude f of theta in terms of your phase changes, your deltas. So in effect, so as a stepping stone, to figure out what your scattering amplitude is, once you know what your f is, you know how everything scatters, right? That's the solution to your problem. But you can translate f in terms of phase changes. So increasingly we're concentrating on what the phase changes are. So we'll do further analysis, try to find formula for these deltas. What are they? All right. Now, so if you know all these phase changes, these deltas, then you know the scattering amplitude, your f of theta. And if you know what f of theta is, then I can put this. It's an important formula from earlier sessions. This is the differential of the cross section, okay, which is f squared. So if you know f, you can plug it in here, times the differential of the solid angle. We talked about that previous several sessions ago. Okay, so once you've got f squared, you can find then the total cross section, the total cross section. In other words, little sigma here, just by integrating this over all possible solid angle, which is 4 pi, of course. That's the total solid angle. That's where this 4 pi comes from. So once you know what f is, and you've got a formula here for f of theta, right, in terms of your phase changes, your deltas. Okay, so if you integrate, if you square, take this term, which is your f of 0, take this term, square it, and then integrate it over all possible solid angle, and you will get little sigma. That's your total cross section here. And I've not asked you to do. Well, you probably. All right. I'll ask you to do. That's not too hard. That's just a bit of calculus. So try that for homework. So square this, integrate over the possible solid angle, and you'll get this result here. Okay, that's by definition the total solid angle. When you integrate this, the differentials of solid angle over all possible solid angle. And the maximum, of course, is just the whole sphere, unit sphere, which is of course 4 pi. Right? So you get this result. Now that allows us to we can then find a relationship when theta is naught. So you get just f of 0, and so f of 0 and sigma. We can get a relationship between little sigma here, and when and for f is 0. Now this term here comes from here. Okay, so when put theta as 0, so you're now cos of 0 is just 1, and the Legendre polynomial of 1 is itself 1. Okay, so this PL of 1 is just 1 here. Okay? So this term drops out, and you just left with this, which is what you've got here. All right. Okay, so now this f of naught. What does that mean? Well, it's the amplitude of when the scattering is 0. This is the wave just the incoming wave just went straight through, did not reflect. So f of 0. So it's just this. Now have a look at this term here. It's a complex number. You know, e to the I x is cos x plus I sine x. That's a complex number. This number here is a complex number. Therefore, this f of naught is a complex number. So let's take the imaginary part of it. I assume you know enough about complex numbers. A general complex number z, usually of the form a real part and an imaginary part. So a real part, let's say little x, and the imaginary part, little y, and your imaginary number, or complex number, same thing, is usually, you know, z is usually written as x plus I, y, I being the square root of minus 1. So the imaginary part of z would be little y. Okay? So if you take the imaginary part of this complex number, in other words, the imaginary part of this, now this becomes cos delta L plus I sine delta L. So if you take the imaginary part of that, you get a sine delta L. Well, you've already got a sine delta L, so you square it. Right? So the imaginary part of this is just this. Right? So this disappears, and you get this, and you square the sine. So you get that. Right? But have a look at this. This is very similar to this formula. Okay? This is the formula for the total cross section. And here you've got a very similar formula, which is the imaginary part of your f of 0. And the f of 0 was called the forward scattering amplitude for sort of obvious reasons. The angle of scattering is 0, right? F of 0, not f of theta. Okay, so have a look at this and have a look at that. So that means you can relate this, the imaginary part of f of 0, to little sigma, which is the total cross section. And what's the difference? Well, if you multiply this by 4 pi over k, you will get sigma. So sigma is just 4 pi over k times this, right? Now this is a rather famous result in scattering theory. So it's given a name, a label, just simply called the optical theorem. What it's got to do with optics, don't worry about it. Okay. This whole these last few sessions and the next few are a bit hand wavy. It's a bit of well, you can't see it. Oh, here you can. Yeah, ICBST. It can be shown that, right? So a bit. Okay, now I need my stool. I don't want to fall off the bed again. All right. Now, in general, finding the values for these phase shifts, these delta L's. Maybe I could do a bit of a reminder. What are we talking about with these phase shifts? Well, as the particle comes in, it depends on the charge of the target. If the target and the particle have the same charge, then the incoming particle will be repelled, right? Like charges repel. And so as it approaches the target, it will decelerate. And then as it moves away from the target, assuming deflected, it will then be repelled still, and it will accelerate. But assuming the target is very heavy, there's no energy transfer to the target, and so the energy of the particle incoming and outgoing, or scattered, is the same, so the de Broglie wavelength is the same. But the phase of the oscillation of that de Broglie wavelength particle, if you like, will change. And that phase difference is your delta. Okay, a bit of revision there. Talked about this before. Okay. Now, calculating what these phase changes, these deltas, are in general is very difficult. So, as usual, you simplify your models so that you can at least say something, so you can solve at least some things, and then take it from there. You walk before you can run, and you have to learn to run before you can fly. Okay. All right. So let's take a simple case. So we'll move on. So we're now trying to find a formula to calculate these phase changes, the deltas. So now we're working on the deltas, right? So let's take the case of fairly low energies, so that the wavelength of the incoming particle is small. Okay. Sorry, other way around. Okay, the energy is small, and therefore the momentum is small, and therefore the wavelength is large. Okay, and so the wavelength is a lot larger than the target. So when that's the case, when your de Broglie wavelength is large compared to the target, then in practice your little L here, remember L is that comes out of angular momentum.